Thank you, Yupen. Can everybody see my slides in presentation mode?
Perfect.
All right, awesome. I had a couple of slides to introduce myself, but you did a great job, so I will fly through those. So today I'm going to tell you about some work. None of this is published. Everything is very preliminary, but I thought this would be a good audience to just show a little bit of the work we have been doing on this front. And I appreciate any comments, opinions, thoughts that you may have at the end or during. So if I say something that doesn't make sense or you have any question during the talk, I'm happy if you unmute yourself and ask, or you go and wait to the end. So okay, let me see, there you go. So as Yupen said, I'm since 2019 at the University of Miami, where I started my lab, which I call the Computational Nanomaterials Lab. So what we do is use multi-scale modeling techniques, theory, and as of recently, data-driven approaches to just to try to figure out mechanisms and fundamental understanding of the structure-property relationship of materials with the aim of eventually designing better ones, right? And one thing my lab and how I think about computation, there is this quote by Richard Hammond that really reflects that, that it says the purpose of computing is insight, not numbers. I guess my bread and butter is atomistic simulations, molecular scale, electronic structure methods. So it's very tempting to try to find a quantitative agreement between experiments and theory. That sometimes is hard, not because the models are not accurate, but because there is many scales in between and things that you don't capture. So I'm more interested broadly on mechanisms and understanding than just getting the Young's modulus of something to the third decimal place. Just to give you an idea of where I come from. Miami, if you haven't been, visit. It's a tropical paradise. Now in the winter is the best months that you can enjoy. And after being 5 years in Chicago, I think I was traumatized for life. So visit. If you ever come by, just shoot me an email. I'll be happy to meet. Here I just have a few pictures of my trajectory. I'm a civil, my background is in civil engineering, like Yupen said. I did my PhD at Northwestern in theoretical and applied mechanics with Sinan. We did a lot of molecular dynamics stuff. I did my postdoc in chemistry. Why is that? Well, it turns out that the techniques that I use are mostly developed by chemists, and they are sort of the best people to learn some of this stuff from. And at Berkeley, I was in this building, Stanley Hall, and there I basically did a lot of electronic structure methods and focusing on the smaller scale problems. So that's me. And today I'm going to tell you about this work we have been doing, trying to understand the relationship between the static structure and the creep properties of classes, which I think it may resonate with some of you. So you're an audience. I hope I don't need to convince you very hard that the structure of materials affects their properties. This is an example I give to high school students when I go and do outreach. You have the same carbon atoms, you arrange them in a slightly different lattice, and you get completely different properties. Now, this is a general statement. It doesn't only apply to the atomic scale, right? You have a structure going from the arrangement of atoms, even electrons, all the way to the macro scale, and all those things matter. So structure is important, right? And defects in particular, this have changed the structure. So by changing the structure, they change the properties of materials. And they do so in a disproportionate way, right? We know that defects, they don't need to be in very large amounts to really control the mechanical properties of systems. And in crystalline materials, which is the stuff that most of us have been, I guess, trained on, or they are more familiar with, these are metals, basically. They have a lattice structure. So defects are very easy to identify. They are very easy to define. Why? Because they break the lattice periodicity, right? These systems, these crystalline systems, are characterized by this long-range order. So anything that breaks that symmetry is very easy to spot. I could say like 99% of the work that has been done on studying mechanics and the role of defects on the mechanics has been on crystalline materials. And the reason is because we have a theoretical framework that can work with that. However, I'm interested in disorder systems. So when you look at glasses, and here I give two examples of atomistic glasses, silica, would be the stuff that the window panes are made of. And metallic glasses are a very exciting new class of materials that have very nice structural properties. So the point here is that when you look at the structure of these things, we don't even know how the effects look like or how to define them. We have very, very little idea of how the structure of these things correlates with their properties, right? It's kind of a mess. And let me do something very quick. So if we want to design these materials, make better materials, understand how their mechanical properties depend on the structure, we need to develop some sort of framework analogous to what we have been doing with crystalline materials, right? And right now we don't have that. So the motivation, the specific motivation for us of studying creep in glasses is actually based on concrete. So creep, you are probably familiar, but a very simplistic explanation of creep is this long-term plastic deformation of a system and their sustained load. And this sustained load is below the yielding point, right? So it's a very interesting, if you think, process, right? It's very highly non-trivial. How can you apply a very low load and you wait long enough and the material flows? So in concrete, this affects the durability of infrastructure. And it's not that creep just leads to catastrophic failure, that it can, but even mild creep can lead to cracking that accelerates degradation processes. So it's a very important process that costs a lot of millions of dollars in repairs. So creep in concrete is governed by CSH. So calcium silicate hydrates are the main phase of hydrated cement, which is the glue in concrete. And it turns out that CSH is a colloidal glass. And the creep behavior depends on the relaxation of this glass under sustained loads. So this is our particular motivation. You'll see that the work that I'm going to show has been done on model glasses. So it still has no resemblance to CSH, but this is where we want to go. Of course, concrete is probably the hardest, more complicated material ever because of the hydration process that goes over a bunch of things, right? So very, in a few years, we'll get there. Now, if you are not interested in concrete, glasses are not a niche material. There is not very few of them. They are everywhere and they are across scales. You can find atomistic molecular glasses, so silica, other inorganic glasses, polymers. Polymers have these amorphous structures. And these are considered glasses because they are triggered, their formation is triggered by a temperature change, right? There is a temperature, the glass transition temperature, below which the dynamics start being very, very slow, and you get the glass. But there is these other sets of materials that are, you can think about jam systems, which span maybe higher scales, and these include colloidal glasses, granular systems, other stuff, traffic, very abstract things that sort of follow the same dynamics. And these other set materials, their transition is triggered by changes in density. You reach a critical density where the system jams. And then once it jams, it does behave like a glass. And when I say it behaves like a glass, is that the similar theoretical framework can describe a lot of the dynamics seen in these very different systems. So in my mind, it's a very exciting problem. So what are we doing towards understanding the structure-creep relationship in glasses? And here I'm going to take a step back from concrete, and we are going to start looking at model systems. So imagine you have a glass. I'm going to call this microstructure, but this could be a box full of marbles, right? You could run. So what I'm going to say now, you could apply to macroscopic glasses. Again, the physics of the interactions, there are some things that are different, but the general framework can be applicable. So you have a microstructure. What does that mean? You have a bunch of atoms or colloids in a box forming a glass in a disordered structure. You can run a simulation. In my case, in our case, we use molecular dynamic simulations, and these are either atoms or colloidal particles, like nanoscale stuff. But again, you could just use other set of simulations and simulate sort of the formation of a granular system. So from the simulation, what do you get out? Well, you get access to microscopic dynamics. So when macroscopic dynamics, I mean the single particle response. And you also get access to the macroscopic response. So this I have it in italics because if you are doing MD, typically the system sizes are small. You use periodic boundary conditions and you take care of the fluctuations because of thermodynamic fluctuations due to the size of the system. You can have access to the macroscopic response of that system, so the bulk response. But in any case, when I mean with macroscopic response, it's not associated per se to size, but it's the system response. So for example, you compress this box of glass and you have a strain over time, and that would be a system response. So our goal is to establish this relationship between microstructure and macroscopic response, right? We want to bypass the simulations altogether. That really is fundamental understanding, something that you don't have to do experiments or simulations to predict, right? But right now we are trying to link just this relationship. Most of the work that has been done on this front and our work, the work that I'm going to present you from the next following slides, it's been trying to relate this microstructure to the microscopic dynamics. Okay, so we are going to work out on this link. Let me frame the problem even a little bit more specifically. So imagine you have a glass, okay? You have a disordered structure, and that's undeformed. Before you apply any loads, we call that the static structure. So the problem, how we frame it is, can we predict if a given particle in the glass will plastically rearrange after just some time based on just local structural indicators? So let me unpack that sentence. So if you take one particle in the glass, okay, and it's this red particle with a yellow sort of boundary, we can measure, we can build local structural indicators. What that means is stuff like metrics that describe the local environment of this particle. The idea is that can we build a model, so some function of those indicators that can tell us if that particle will plastically rearrange or not. We'll talk a little bit more about what this plastically rearrangement means, but in a very general sense, you can basically classify particles in two types. One is hard. These would be particles that upon deformation, they don't displace a lot. They are actually moving in their own sort of local minima. And then soft particles are those particles that undergo large rearrangements, and we call those plastical rearrangements. So the problem becomes, so if you have a structure, you derive some local structural indicators, you can build a model, and then you predict whether a particle is hard or soft. You can go in the simulations and check whether you were right. Okay, so that's the framework. That's the problem that we are going to be working on solving. So what do we know so far? Well, we know that simple structural indicators do not correlate well with the particle response. I will show you some quantitative information about what this means. So a simple structural indicator would be, for example, the number of neighbors within some cutoff distance. So if you try to predict whether a particle is hard or soft based on that simple metric, you are not going to be able to do that. Your model is going to be very terrible. So people have been trying to find this correlation, so what I call here model f of xi, forever, right? And we haven't been able to work on that. So what has been happening in the last maybe 5 years or so is that people have been turning to machine learning. It's like, okay, simple structural indicators are no good. They don't correlate well with the response. So can we use machine learning to find potentially complex indicator? Machine learning is good at finding these hidden patterns that actually can help us with this hard-soft classification problem. So here, machine learning will replace the role of the model, which typically is just a function of some local indicators. So this is the problem that we are going to solve. Now, in the rest of the talk, I'm going to tell you about the relevant things about this problem. One is the data collection. What kind of simulations do we run? Where do we get the data? What kind of data we get? The other one is the particle response, the macroscopic response, sorry. I'm telling you that we are studying creep. It's not very clear that you can study creep using molecular dynamic simulation. So we are going to see what kind of response the system gets in our simulation. So how does this strain over time depends on temperature and applied stress. We are then going to start looking at the microscopic dynamics. Just remember that the problem that we are trying to address is this relationship between the static structure, so the local structure of the particles, and their dynamics. So in this microscopic dynamics, we are going to have to also discuss how we are going to label particles into soft or hard. Okay. Finally, I'm going to tell you how we are using machine learning to make some predictions as to whether these particles will plastically rearrange or not. Okay, so let's start with the simulations. So what we are using is a Cobb-Anderson model. This is a glass model system. These are two types of particles interacting through a Lennard-Jones potential, this 12.6 Lennard-Jones potential. And the reason there are two particles interacting through these interaction parameters is that if you have a monodispersed Lennard-Jones system, it's going to crystallize, right? So the Cobb-Anderson model is, you can think about it as being the minimal model that can give you a glass, okay, a disordered structure. And it's called 80-20 because there is 80% of particles of type A and 20% of particles of type B. Again, the details don't matter as much as saying that we have a model system of a glass. Now, the simulation protocol is very simple. Don't even look at these details. We just subject the system to uniaxial compression. So the parameters here are an applied stress, which we make it below the yielding point, obviously, and the glass is at a certain temperature, which is also well below the glass transition temperature. We do that because we want to study creep and we want to study the glass dynamics. All right, so these are our simulations. Yes, uniaxial compression of these systems. The systems that we simulate have 10,000 particles. And so far we have simulated 10 different initial configurations. So when we prepare the glass, we generate a melt and then we cool it down. Right, so that process is very stochastic, especially at high temperature. So we repeat this process 10 times, which results in 10 different initial configurations of the glass. Now, for each initial configuration, we perform 15 independent runs. Okay, the difference between one run and another. If you know anything about molecular dynamics is actually a deterministic algorithm. So what we do here differently is that we assign a different random distribution of velocities to the particles, right? So again, the configuration is the same. When I say configuration, is the X, Y, Z positions of the particles initially, but the distribution of velocities is different. So that leads to actually different response of the system. Okay, so how does the macroscopic response look like? Well, it looks like this. So here what you are seeing is a strain versus time, the number of steps actually. All the units here are sort of monopoly units, Lennard-Jones units. They have related to the Cobb-Anderson glass, so they are not going to make a lot of sense compared to, you know, megapascal, gigapascals or things like that. So when I say that the stress is 0.5, important part here is that the yield stress, for example, for the Cobb-Anderson glass is 1.2. So, and the temperature that we simulate is very well under the glass transition temperature of the Cobb-Anderson glass. So the thick black line that you see here, that's the average response over all the configurations and over all the runs. Okay. And the shaded black line that you see is the standard deviation, is one standard deviation in the response. So what you see is a quick elastic response. Okay. And then logarithmic creep. Now, this is like almost textbook logarithmic creep. So what we are probing and all the statements that we are going to make from now on are about primary creep. Okay, we don't have access to secondary creep. This is what we can get with simulations. But whatever we, find should be applicable broadly to primary creep, where again, the strain depends logarithmically on time. So I'll show you some plots that we have about how the response, the microscopic response, depends on the applied stress. So you can quantify the macroscopic response, two parameters, for example. One is the elastic response, or the Young's models that you could derive from that elastic response. And the other one is the creep modulus, which is this C here in the formula that you see. So what we find is this relationship. So basically what these two plots mean is that below certain stress, the results don't change much. You have a material that shows the similar creep modulus and similar Young's modulus. Now, when you go to higher stresses, and again, the yield stress is 1.2. So when you go to higher and higher stresses, you get dynamical effects that we are not very interested in investigating right now. So what we want to do is be safe and use stresses that are below the point where dynamical effects start taking place. All right, so this is the macroscopic response. What we need to learn from here is that we are probing primary creep. Now let's look at the microscopic dynamics. So we quantify the microscopic dynamics in two ways. Well, it's one way, really. It's looking at the non-affine displacements. You have a box full of marbles that are deforming. The box is deforming. The marbles are moving. So the best way to characterize how much they move and when they move is non-affine displacements. So these are basically displacements where you subtract the bias of the overall deformation. We have two different measurements. One is global non-affine displacements. So these are calculated with respect to the global strain of the system. And then local non-affine displacement. This is a metric that Falk and Langner came up with in '98, which is widely used in granular systems. And it measures local deviations from affine deformations. So this is a local measure, right? So what you are doing basically is calculating a strain tensor around the particle and seeing how that particle has moved with respect to that affine stress tensor. So we have these two metrics. How do they look like? Let's take a look at the statistics. So if I plot here in these plots, what you have are on the left, local non-affine displacement, on the right, global non-affine displacement. On the top, you have both are, so the four plots are the probability distribution of the displacements. So on the top, you have them in the linear scale. And in the bottom, you have them in the semi-log scale. So the things that I see here is that over time, again, these displacements are measured with respect to the initial and the form configuration. So if you look at the top left plot, okay, over time, this would be going from blue to green. The distribution becomes broader and the average displacement shifts to the right, okay? Also, the tails become thicker. Okay, so you get, this makes sense, right? As you deform the material, the displacement of the particles with respect to the initial deformation sort of increases, right? That just makes sense. Now, the local and global displacements, they show the same trends. They look slightly different because they are different measurements, but they show the same trend. Now, what you see in the bottom is the logarithmic scale in the y-axis in probability. Why? Because here you can clearly see that these distributions of displacements are characterized by very, very fat tails. Okay, so this is important because it tells you something about the physics of the system. How people have interpreted this is that, look, you have, if you look at the tails, they start taking over when the probability is just below 10 to the -3 or 10 to the -4. So what this means is that most of the particles, 95% of the particles actually undergo very, very small rearrangements. Their displacements are pretty small. And then some particles move a lot. And those are basically the ones that constitute the fat tails. So the fat tails here are very significant. So this is sort of the basis why people started thinking about, particles in a glass under stress or temperature having two populations. And that these are the populations that we are going to call soft and hard. Okay, so hard would be particles that don't rearrange, soft will be particles that rearrange. So that, is hand wavy at best, because you should still have the questions like, okay, sure, I buy your argument that the fat tails are the soft particles, but still these are unimodal distributions. So where do you put the limit? What's your threshold to say, hey, if displacements are higher than this number, you have soft particles. If they are smaller than this number, you have hard particles, right? This is kind of an arbitrary threshold. And in fact, people working on this problem, that's exactly how they treated this as an arbitrary threshold. So here I'm showing you 3 different papers, very good, very high quality papers, where they are working on the same problem. It's trying to classify these particles in the glass as soft or hard. And they have to set this arbitrary threshold, which actually changes in each study on the d-mean square displacement, which is the local non-affine displacements. And sometimes it's honestly kind of weird. For example, in the study on the left, you see that the threshold is selected such that in terms of real length units, it's about 12% of sigma. Sigma is the length scale of your particles. I mean, I don't know how it sounds to you. To me, it sounds like a very low limit for a plastic rearrangement. Like you move basically 1/10 of your diameter. And in this study in particular, they already consider a plastic rearrangement. So there is, the point here is that there is arbitrary thresholds. You have to choose something, and there is no, we don't have the right answer right now. In fact, in this study on the top right, they developed some sort of rational, at least system to determine the threshold. They are saying, okay, we don't know, we don't have a physical grounds to determine a particular threshold. So what we are going to do is train a machine learning model with a bunch of different thresholds and just select the threshold that give us the best accuracy in the classification. So this actually is a rational scheme. It's not very satisfying from a physical perspective, because it feels that there should be something there that tells you what particles are rearranging and which are not. So we found this very unsatisfying. So we developed our own different system to label particles. And it's actually based on the global non-affine displacements. So what you are seeing here is the distribution of the global non-affine displacements just on the X direction. That's why you see negative and positive, and this is symmetric, right? So here, why is this curve better than the other curves? Well, it's better because I can fit a Gaussian curve to the data, okay? And I can see where the tails actually deviate from the Gaussian. If you think about a normal distribution, what the meaning, physical meaning of a normal distribution is that the particles sort of offer a diffusive behavior, right? That's what you would expect from diffusive behavior. And whatever falls outside that, it's something extraordinary in the sense that cannot be explained just based on diffusive behavior. So we are going to use this criteria to actually label particles as soft as hard. So what we are going to do is take the probability distribution of displacements for X, Y, and Z. We are going to feed a Gaussian to the displacements, and we are just going to classify particles outside that don't fit the Gaussian as soft, okay? There is no moving parameters in this scheme. We are just feeding a Gaussian to the displacements of the whole population of particles at some time. We don't have a threshold. So we think, and we have a physical justification. So we think our labeling scheme is significantly more meaningful than other arbitrary labeling schemes. It offers some very interesting advantages. So here, the physical meaning of our criteria is that particles are classified as soft when their displacement cannot be explained based on the diffusive dynamics of the overall population. That's our criterion. And what this can take into account, implicitly, we haven't tested, but it's promising, it can maybe take into account effects of temperature or stress that basically affect the whole system similarly, right? Other materials, if you think about, let me go back to this slide here. So if you think about choosing a fixed threshold to quantify soft or hard particles, you see that the curves of displacement move over time. So that threshold will change over time as well. So we need something dynamic that actually can identify soft particles as the system evolves. All right, so let me show you, let me talk about something very quick. So these are fluctuations, and what limits do they impose on the prediction of the static structure? So, okay, so just bear with me. I know I'm going very fast, but bear with me. So you have a particle in a glass, and you have the same initial configuration, okay? You stop the simulation after the same number of steps, and in different runs, which again, the difference between the runs was just the initial distribution of velocities, you can have a slightly different behavior. What that means is that if I classify the particle, this particle, as soft or hard for many independent runs, they won't be 0 or 1 for all of them. Okay, so at the end of the day, I can take an average, and that average would be the probability that that particle is soft. So I'm calling soft particles 1 and hard particles 0. So a probability that a particle is soft close to 0 means that the particle is probably hard. So people call this propensity. Okay, and I'm not gonna go into the details because this is a very interesting, complicated conversation about the role of fluctuations in small systems, but also fluctuations in glasses. So you have thermodynamic fluctuations that we know they scale with the system size. So these are basically just statistical uncertainty. You know you can get better if you run more simulations or you run larger simulations. So this is not, thermodynamic fluctuation is not something that you should be worried about too much, unless you have to make a quantitative prediction under a certain threshold of uncertainty. But thermodynamic fluctuations we can work with. However, in glasses, there is this other thing that is called dynamic heterogeneity, which is associated to transient spatial fluctuations in the local dynamical fluctuations. So these are fluctuations that are intrinsic to the glass dynamics, and we cannot get rid of them. They are part of the system. So it makes, you know, working with glasses complicated because it's not a right or wrong 100% deterministic. You always have these intrinsic fluctuations sort of creeping in. Okay, so what I'm going to show you from now on in the next slide is I'm going to show you some statistics about how these labels work. And when you see values that are not 0 or 1, they are actually something in between. They have been calculated for an averaging over the 15 independent runs. And that's the reason why we run independent runs. Okay. So how do these statistics look like? Are there a lot of soft particles, a lot of hard particles? So the probability distribution of the probability of being soft is power law distributed. What does that mean? That you have a very high probability that you find a particle in the glass that is hard, okay? Those are probabilities of being soft very low. And then you have very, very, very low probability, and again, it's power law distributed, that a particle is soft, okay? What does this mean? That there is a very small minority of particles in the glass that can be considered soft, that actually they plastically rearrange when you subject the glass to creep. So over time, what you see the 3 colors here is for different times. So blue would be soon or early, and green would be late. So over time, the soft particles become less and less common, okay? And I'm going to show you something now that we are very excited about. I'm going to skip these statistics, and I'm going to go to the actually very interesting discovery. So if you plot the fraction of soft particles, how we have defined them as a function of time, you find that they also, their number decreases logarithmically in time. This is exactly how the strain decreases in primary creep. So what this suggests is that there is, again, it's not a proof, right? But this suggests, and we are trying to find ways to prove it, that the soft particles, even though they are less than 5% of the system, sometimes much less than that, here the fraction of particles is 2%, they seem to be controlling the creep response, the creep rate of the system, the deformation rate of the system. This is very interesting because they start looking like defects, right? In crystalline solids. Defects in crystalline solids, they don't need to be very common or very frequent or very abundant in terms of the overall bulk material, but they do govern the response. And what we find is that these soft particles, at least they correlate perfectly. Again, I don't have causality here, but they seem to control the creep, or it's a hypothesis that they control the creep in concrete, in glasses, sorry. All right, so we have a way to label particles into soft and hard. Now, the next thing I'm going to show you is how do we determine metrics to characterize the local structural environment of the particles. Okay, so there is in the literature 2 widely used local structural indicators. Again, local structural indicators, what are they? Is for a given particle, here the particles indicated as C in red, you want to come out with numbers that describe the local structure. So these numbers could be the distance between the nearest neighbors, between that particle and the nearest neighbors. You can measure interstice areas between 3 particles. You can measure interstice volumes. You can measure those with the nearest neighbors. You can measure those with the second nearest neighbors. You can calculate a lot of these simple metrics. And this could be exactly what those local structural indicators mean. Another set of functions that you can calculate is just these symmetry functions. These are slightly, they are close if you want to think about a radial distribution function. So they are functions that are related to that. They are symmetric in space. and they basically measure the relative density of other particles with respect to the particle that you have. So you can measure these things, you can plot them, and you can gather, a numerical vector with that information. So again, that gives you information about the local environment, the local structural environment of a given particle. So how do these local structural indicators correlate with the labeling? So whether a particle is soft or hard? Well, this horribly. So what I'm showing you here is in the x-axis, you have a bunch of features or local structural indicators based on short-range order and medium-range order of the classes. So the details are not important, but in the x-axis, each of these bars is basically a simple structural indicator. And in the y-axis, you have a Pearson correlation coefficient between this indicator and the labels between soft and hard. So what we find is like an extremely poor correlation, right? All these parameters are below 0.1. Okay, so you would never try to develop a model, using these indicators and independent variables because the correlation is so bad that what are the hopes that you get something right? So the magic here comes with machine learning. And this is what people are trying, and what we are trying is like, okay, can you take a bunch of crappy local structural indicators, use a machine learning model, and do better, have an actual reasonable prediction? And the hope here is that each of these individual structural indicators doesn't correlate well with the behavior of the particles. However, there must be some function of this that can be complicated. So some function of the local structure of the atom that determines whether it's soft or hard, right? That's the hypothesis. So the way you prove this hypothesis is by training a machine learning model and seeing if you get predictions that are non-trivial. So the machine learning predictions, I'm not gonna go into details, and you can ask me if you are interested of how we develop the model and all that. So let me tell you the data that we use. We have 8,000 particles of type A. We are focusing on type A particles in the Cobb-Anderson class. And we have 10 initial configuration. So each particle in our case, we want to classify as hard or soft. So we have 80,000 examples to train the model. Again, the labels are hard or soft and are calculating using 15 independent runs, right? So we calculate this propensity between 0 and 1. For features, which are the local structural indicators, we use these short range order features and medium range order features developed in this paper. And the challenge of the classification, this is a non-trivial problem. Why? Because you are trying to classify particles as soft or hard, but it's a highly imbalanced data set. Typically about 1%, but always less than 5% of particles are soft. So it is a hard problem. And these are some results that we got recently. Again, we are working on trying to optimize the model. But what you see on the table on the left is a very common logistic regression classifier. And the different rows are different sampling schemes. These are advanced techniques to try to deal with the imbalance in the data set. And on the right, you see different models in the rows, support vector machines, logistic regression, random forest reading, boosting descent, different models in the rows, and using just the random undersampling scheme to deal with the imbalance. I'm not gonna go, these are just names for you, right? This is not very important. What is important from this table overall is that a classifier with no skill would have a scores of 0.5, okay? So given these features that didn't correlate with the labels at all, the machine learning models are actually able to make predictions that are non-trivial. And they are around the 65%, 70%. So they are accuracy of classification of 70% based on these features is actually pretty remarkable. So we are working now on trying to, how do we optimize these models? What is our best prediction possible? Okay, so that's the last slide. Let me summarize the talk a little bit. I know I went quite fast, so I'm happy to take questions after this. But I hope I show you that we can access primary creep of Cobb-Anderson glasses using MD simulations. Okay, that's our domain. When I talk about creep, I mean primary creep because this is the only regime that I can access with my simulations. Now, I show you that the particle dynamics are characterized, so the non-affine displacements are characterized by long tails, which suggest the existence of soft and hard particles, okay? We develop a new labeling scheme to classify particles as soft or hard that does not depend on arbitrary thresholds. In fact, the only thing that it depends on is this assumption that the population behaves diffusively. And you can see that because they fit within a Gaussian. Now, the number of soft particles, I show you how we label them. It decreases logarithmically in time, which suggests that these soft particles being much less than the hard particles, less than 5% of the population, may govern the creep response. And this starts sounding like defects to me, okay? Finally, I show you that simple structural indicators cannot predict the particle softness, but machine learning models actually give rise to non-trivial predictions, okay? So that's what I have for you today. And thank you for being here. And I'll take any questions that you have.